Welcome to the lecture for Section 10.3, Optimization in Business and Economics for Math 1325. What we're going to look at today is what is optimization and how do businesses and social services use it. And then we're going to rely upon what we learned in earlier sections of this chapter about how to use derivatives to find optimum values. So optimization is quite an intuitive process. It's really just anything that is trying to make something better, more fully perfect, more functional, more effective as possible. And this could be anything. You may want to optimize your study habits so that you get better grades. You want to optimize the performance of your car so you get better gas mileage. So this, it's a very intuitive idea that hopefully is part of just general knowledge as well. And then also pertaining to this course, it's the mathematical procedures that we use to find those optimum values. So think about it for a minute. What might a business want to optimize? Obviously, a business wants to make money, so they want to optimize their revenue streams, which means probably maximizing revenue and minimizing costs so that they ultimately will maximize profits. What about a hospital? Well, depending upon where you are, you might want to, again, you might be looking at it from a cost perspective. So you might want to minimize stays in the hospital after a surgery. You might want to look at it from a healing perspective. So you might want to, again, minimizing the days you have to stay in the hospital might be something related to the effectiveness of a surgery or therapy. You might want to minimize the number of days of recovery, whether in or out of a hospital. Minimize infection rates. You might look at it from a legal perspective. You might want your hospital to have less lawsuits, etc. So there's a number of things we might try to optimize from a hospital's perspective. The police department, again, do not think in terms of very limited areas. There's lots of areas that any organization might want to optimize. Certainly we want to perhaps lower the crime rate if we're a police department. But there may be things that we need to optimize in order to do that. Maybe we need to have it, we want to maximize our presence in communities. Maybe you want to maximize face recognition for specific police officers in a community. This is a community policing initiative where you actually have specific officers assigned to a limited area, like maybe a square mile area, and they're walking a beat. This is kind of old school police. So there's a lot of things we can look at for optimizing. And so don't just think in terms of cost or the most immediate function. There's all different levels of complexity in any situation. Absolute extrema, okay? In the last sections, we found relative extrema, minimums and maximums. And if you remember the graphs that we looked at, they had peaks and valleys, multiple ones of them. But now we're trying to focus on the absolute extrema, the absolute extreme values. That's all that means. So an absolute extrema is the functional values that are the largest or potentially smallest over the entire domain of a function. So here, instead of just looking at where there are peaks, if it's a maximum, or valleys if it's a minimum, we're going to look at, if we're looking for the absolute maximum, we're going to look at all the peaks and see which is the highest. This is very intuitive. Or if we're looking for the absolute minimum, we're going to look at all the valleys and see which one goes the lowest. So again, very intuitive, etc. Remember that when we're talking about maximums or minimums, that the y value is always the functional value. So if we're trying to maximize costs, we're going to look at the y values. How high up does the graph go, or how low does it go? So that's why you see the notation here is f of a. Remember, this is functional notation, and f of a is just another representation for the y value when x equals a. So it says here that f of a is the absolute maximum if f of a is greater than f of x for all values of x. Now again, all this means is that if you're looking at a graph, it is the highest peak. And the same for the minimum. If f of a is the absolute minimum, if f of a is less than f of x for all values of x. And again, if you're looking at a graph over the entire domain, if you can see the entire thing, this is going to be the lowest valley. Okay, so again, this is pretty intuitive. Notice these three graphs are actually all the same function. They just have different domains. So this first graph you see perhaps over all values of x. The second one is only between x is 1/2 and x is less than or equal to 2. And this third one is between, here you can see it's between 2 and 3. Okay, so notice in the first graph, there's no absolute maximum because the graph keeps going up and up and up and up to infinity. So we don't have an absolute maximum. We have an absolute minimum, which is the valley, the only valley we see here, and that's at the point of 1, 0. X is 1, y is 0. And so again, remember the absolute minimum value is the y value, or 0. The absolute minimum point is the vertex 1, 0. This is an x and y coordinate. So see if you can determine, hit pause for a minute if you need to, what are the max and minimums, the absolute max and the absolute minimum for B? Again, hit pause. Here's a little reminder. Remember, the x value tells you where the extrema occurs, or the max or minimum occurs, and the y tells you the value of the extrema. Okay? So let's look at graph B. Notice that we have an absolute max point. Now because we've limited to the domain, the graph does stop at the point 2, 1. This is the highest point, as we can see on our graph, 2, 1. So that's the absolute maximum point. Again, the absolute minimum point is again at 1, 0. That's the lowest point on the graph. So we have an absolute minimum point at 1, 0. Again, these are the points for the maximum and minimum. The absolute minimum is the y value of 0. The absolute maximum is the y value of 1. And this is for graph B. So when we've limited the domain, we put it over a more, instead of all x that we see in A, we have just between 1/2 and 2. Now we have a max and a minimum point, and an absolute max and an absolute minimum. Okay. Notice that in A and B, the absolute minimums do coincide at 0. What do you think is going to happen at C? See if you can figure out the absolute max and the absolute minimum points at C, for the diagram in C. Here, we no longer are going through the vertex, which is at 1, 0. But we do have a high point. Again, we can just look at the graph. The largest point, the highest point on the y-axis is the absolute maximum point, and that's at 3, 4. The absolute minimum point is at 2, 1. Because our graph now goes between 2 and 3, we no longer have the minimum point at 1, 0. Okay, so our absolute minimum in graph C is 1, and the absolute maximum is 4. So notice, although we're graphing the same function, we can have very different absolute max and absolute minimums depending upon the domain that we select. If we limit the domain to a certain part of the graph, we get different absolute maxes and minimums, and sometimes we didn't have any absolute max because the function continued on. So this is very important to pay attention to what's happening with the domain. Okay, and we're going to learn a strategy for examining this that also includes the derivatives that we learned earlier. So when evaluating a function with a limited domain, that just means that we're specifying not all values of x, but a range of x. Notice in A we had all values of x. Here we had just x between 1/2 and 2, etc. as in graphs B and C below, be mindful that in order to find the absolute extremas, we need to compare both endpoint values and critical values. All right. Now remember, critical values for maximums and minimums are where the derivative, the first derivative, equals 0. Okay, so that's what the critical values were. That gave us the x values that we would then plug in. For example, here, when we plug, if we found the derivative of this function, we would get that that derivative equals 0 when x equals 1, because that's where the vertex is, and we can see that the derivative is negative here and positive here, so it's going to be 0 at 1, because it's also going to be, the tangent line is going to be horizontal. Okay, so we would find that point, but we would also then compare the endpoints. And what does that mean? Well, looking at graph B, what we would do is, again, we'd find that point, so we'd have one critical value point, which is 1, 0. We would then plug in the domain endpoint. So we'd do f of 1/2, or we'd calculate what y equals when x equals 1/2. 1/2 minus 1 is negative 1/2. Negative 1/2 squared is 1/4. We'd also plug in 2 into y equals x minus 1 squared, and we get 2 minus 1 squared is 1. 1 squared, excuse me, 2 minus 1 is 1, and then that squared is also 1. We would compare those three values. Now, we can easily see them here on the graph that the max is here at 2, 1, the min is at 1, 0. But if we plug these in, all we do is look for the largest value of y, and we would see that that would be 1, and that would be our absolute maximum. And it would occur at x equals 2, and we look for the smallest value of y, or f of x, and that's 0. Okay, so that's all this is saying, is that if you have a limit on the graph, besides finding where the derivative is 0, you also plug these values back into the original equation and compare them. Okay, I guess I should have clicked earlier. All right. So let's look at a problem. The total revenue in dollars of a firm is given by R of x equals 8,000x minus 40x squared minus x cubed, where x is the number of units sold per day. If only 50 units may be sold per day, find the number of units that will maximize revenue. So first of all, it gives us a limit here on the x value, right? Because we know that x is the number of units sold per day. So what is our domain? Well, first of all, we can't sell negative units, so x has to be 0, because we could sell none, or higher. And we know that we have a limit that we're only allowed to sell, or we can only sell 50 per day. I'm not sure why that would be. Maybe we're a regulated industry. Let's just say that. Okay? So notice that our domain is from 0 to 50. That is, x has to be greater than or equal to 0 and less than or equal to 50. Okay? This is in interval notation. X is greater than or equal to 0 and less than or equal to 50. You could have also done it with inequalities. 0 less than or equal to x, less than or equal to 50. So we know that the maximum will occur at either an endpoint, that's x equals 0, x equals 50 from our domain, or at a critical value. Remember, again, this is where the derivative equals 0. So let's find that part first. Again, you can pause this now and see if you can do this on your own, and then hit play again and pick it up when you're done the problem. And I do recommend you do that for all of these. I know it's easy just to watch, but if you're anything like me, often I'll watch something and go, oh yeah, I got that. That was pretty easy. And then later when I try to do it on my own, I go, how did I do that? So again, I highly recommend you hit pause on all of these. All right, so let's take the derivative. Now this is a very easy derivative. R prime x, or the derivative of R of x, equals 8,000 minus 80x minus 3x squared. Okay. So notice I plug in, I set this equal to 0. Notice I have a quadratic equation. Negative 3x squared minus 80x equals 8,000, or plus 8,000. So I can solve this by either factoring, or I can plug it into the quadratic formula. And that's what I've done here, and I find out that x equals 40, or x equals negative 200 over 3. Now remember, that our domain says that x has to be between 0 and 50 because we can't sell a negative item. We also can't sell a fractional unit. That'd be like selling just part of the TV, okay? So the only value that's valid is x equals 40. So now I have three values to compare, 0, 40, and 50. So I'm going to plug those all values back into the original equation and see which is the largest. Okay? Now the easiest way to do this is to plug the original equation into your calculator, okay, using the y equals function. So plug this in and then go to the table function, which is above the graph button, using the second function, and then you can just go through the table and look at these values all at once. So when r equals 0 and we plug that in, we get 0. When x equals 0, the revenue for that day is also 0. When we plug in 40 into the r of x equation, we get the revenue for that is 192,000. And when we plug in 50, we get the revenue equals 175,000. So we can see here that we get a maximum revenue of 192,000 when we sell 40 units. So be careful, because this didn't ask us to find the maximum revenue of 192,000. It said find the number of units that will maximize revenue. So this answer to the left is wrong. The answer, max revenue of 192,000. I mean, technically we did make that revenue, but that's not what the question asked. Pay attention to the question. What the question asks is how many do we have to sell to make the maximum revenue? So the answer to this question is that max revenue occurs when 40 units are sold. Although it says wrong above here, it means that this answer was wrong and that this answer is right. Sometimes my slides are a little bit cray-cray, huh? All right, let's move on. So again, I highly recommend that you pause here. Actually, don't pause here. This is a kind of a confusing problem, so let's do this one together. A travel agency will plan tours for groups of 25 or larger. If the group contains exactly 25 people, the price is $300 per person. However, the price per person is reduced by $10 for each additional person above 25. What size group will produce the largest revenue for the agency? This is kind of confusing, and when you see it in table form, it's actually not quite so bad, but like when you read that data, it's hard to figure out how do I do the math to figure this out. A great idea is to actually do examples, because normally we could figure it out like we know that when there's 25 people, we can easily figure out the total price, okay? And what we're trying to do here is maximize the revenue, okay? So remember that the revenue for anything is simply the number of items sold, in this case, I guess it's tours, and the price per tour, all right? So it's just price times quantity. So we first need to figure out the equation. So if I did this kind of table, now I know that if I put 25 people in a group, that the price is 300, so I'm going to get 7,500. Notice it says the price per person is reduced or dropped $10 for each additional person. So if I have 26 people, and I'm writing this in terms of a number so I can figure out a formula at the end. If I have 26 people, my price is now only $290. And again, notice I'm putting the math in here, and I'm doing this very intentionally because most of us would intuit, okay, if I have 26, this is now $290 because it's 10 less. But it's better to see the math so that I can figure out a general formula that we're going to get to. If I have 27 people, which is the original number, plus 2, notice that my price is now gone from the original price down by 20. What I'm doing here is I'm trying to identify patterns. So when I add 1, I subtract 10. When I add 2, I subtract 20. And so I'm starting to see the pattern here that when I add a variable, x, to the base number 25, which is where we started. Remember, we're only going to do groups of 25 or larger, so my domain is greater than or equal to 25. Notice that when I add any specific number above, actually that's not true, is it? We start with 25. X can be X just has to be positive, okay? Be careful there. X doesn't have to be 25 or greater because we're starting with 25 as a base number, not the X. X can be 1, 2, etc. But notice that what we've done here is for every person we add, we subtract 10 times that number from that base price. So as we can see, the number that we have in our group times the price per person gives us the revenue. So if the number in our group is 25 plus X, and the price per person is 300 minus 10X, and we got that from looking at the patterns, then our total revenue is this, 25 plus X times 300 minus 10X. But don't get confused here. All that is the price, 300 minus 10X, times the number of people on tour, 25 plus X. So now we have our functional revenue equation. So with that, we can figure out the endpoints and also the critical values for this equation. All right. So when we multiply this out, we get the revenue function is 7,500 plus 50x minus 10x squared. When we take the derivative, again, a very simple derivative, we get 50 minus 20x. And notice that what we get here is that the derivative equals 0 when x equals 2.5. Now this is a little bit problematic because remember x is the number of additional people. So be careful. We're not saying we have 2.5 people on the tour. We would actually have 2.5 more than 25 or 27.5 people. So this again is problematic for another reason, is that we don't do half people. Okay, it's kind of gross. It would be like a Freddy Krueger, tour, which actually might be kind of popular. Anyway, let's move on. So we can't have half people. So let's look on each side. So we have 27 people. We plug that into the original equation. Remember, we're always going back to the original equation. We're trying to maximize revenue. The R of X equation is the revenue equation. What does the derivative tell us? You remember? How fast the revenue is changing, instantaneous change. How is the revenue changing with each unit sold? Okay, so we also plug in 28. We plug in a value on each side of 27.5 people. So we get 27 or 28. And notice it doesn't change. We get max revenue for 27 or 28. That's a very unusual thing because you'd figure on a tour you'd have incremental costs. But, math teachers like to set up problems that are not too complicated, although they sometimes do seem that. All right, so in this problem, our revenue is maximized when either 27 or 28 people go with us on tour. All right, let's try some more practice. And this time I do want you to push pause and try this on your own. All right, the price of a product in dollars is related to the number of units demanded daily by P equals 168 minus 0.2x. Okay, now remember in all of these, P is price, X is the number of units. The average daily cost for this product is 120 plus X dollars. How many units must be sold daily to maximize profit? What is the selling price at the optimal level of production? And what is the maximum possible daily profit? All right, let's take these one at a time. How many units must be sold to maximize profit? All right, so here we have the price of a unit. And remember, well, hold on, let's slow down a little bit. Remember that profit equals revenue minus cost. Okay? And remember that revenue equals the price of a unit times how many you sell. Okay? So let's look at that. And also, I'm sorry, I went blank there for a minute. We have the average daily cost, and we want to know the average cost times the quantity. Okay, so this is this is kind of a little bit confusing because it's not the average cost per item, it's the average daily cost, but we're going to make X items each day. All right. So revenue equals price times quantity, cost equals average cost times quantity. So let's figure out what the profit is. So profit is the revenue price times quantity, this times x, minus the cost, which is the average cost, times the quantity. And when we do our simplifying algebra, we get 48x minus 1.2x squared. Okay, this is our profit function. We're trying to maximize profit, so we take the derivative, and notice that the derivative equals 0 when x equals 20. Okay. So when we plug, this is the second derivative test that we learned from the last chapter. This is just to test that the optimum value here is a maximum and not a minimum. Okay, so this is a second test we can do to make sure that this value, that when the derivative, the first derivative equals 0, that this value is actual maximum. Because remember, if the second derivative is negative, then we have a maximum there. Okay. And again, our question was just, it wasn't what is the maximum profit, it just tells us how many units must be sold daily to maximize profit. So we're done there. We don't even have to figure out what that maximum is. All right. The selling price at the optimum level, again, the optimum level is when that's going to be equal to 0, right? When our derivative is equal to 0, and we already figured that out. So all we have to do is put this back into the price equation to figure out what our optimal price is, or our selling price at the optimum level. Plugging in x equals 20, we get that the optimum selling price, or the selling price at the optimum level, is $164 per unit. What is the maximum possible daily profit? All right, so it did ask us for the maximum profit, which is from the equation in A. All we have to do is now plug in the value again, 20, back into our original profit equation, which is here, and find the value, and we get $480.